This is the venom from one of the world's deadliest snakes, a saw-scaled viper. There's enough here to cause a slow, agonizing death through massive internal bleeding, shock, and organ failure.
There are real challenges in managing these patients and supporting these patients.
More than 2 million venomous snake attacks are reported every year, causing around 140,000 deaths. There's enough venom in here to kill up to 10 people. Snakebite medicine hasn't changed in over 100 years and still uses horse's blood for treatment. It's Victorian medicine.
It's really in the last 15 years or so that there's been really major changes in how we actually approach treating snakebite.
The antivenom they've produced is a potential game changer.
Yes, I do believe over the years we could save hundreds of thousands of lives.
This is one of the largest collections of venomous snakes in Europe. More than 160. From 50 different species. From cobras to mambas and puff adders. These reptiles are helping scientists at the Liverpool School of Tropical Medicine to learn more about venom, the way it works to kill prey or defend against predators. And it's this vital research that has brought the world one step closer to finding a safe, effective antivenom.
So LSTM has probably got the biggest concentration of snakebite researchers in the world, and that research goes all the way across from understanding what a venom does in the laboratory to improving the systems and training for health professionals that will give treatment to patients. What we're trying to do really is understand, first of all, venom effects, and then look at how antibodies, immune responses, or drugs can treat those venom effects, ultimately humans, and then how do we deliver those treatments to those humans over time?
More than 2.5 million people are bitten by venomous snakes every year. Of these, around 138,000 will die, and some 400,000 survivors will be left with permanent disabilities, including amputations, blindness, and severe tissue damage. Most people who are affected are farmers, women, and children in rural Africa, South Asia, and Latin America. India alone loses 58,000 people to snake bites every year. That's more than the population of a small city. Other countries which are most affected include Pakistan with over 2,000 snakebite victims, Nigeria with nearly 1,500, and Bangladesh with more than 1,100.
Namaste. Namaste.
But despite this devastating toll on lives and livelihoods, snakebite is a disease that the world has largely ignored. The World Health Organization classified it as a neglected tropical disease in 2017 and set a target to halve the number of deaths by 2030. But the way antivenom is produced now is the same as it was 130 years ago, by injecting snake venom into large mammals like horses. The antibodies produced in the animal's blood are then used to produce antivenom. But this treatment can also present a serious risk to the patients.
It works. It can neutralize venom, but I would say almost, of course, when you take something from an animal and inject it into a human, the human immune system will see it as a foreign substance. So it's not a question of whether you'll get adverse reactions. It's more how severe are they? Will you go into full-blown anaphylaxis and actually die from the antivenom treatment? So it's a mix between antivenom could be better in terms of neutralizing a broader spectrum of snakes, could be cheaper so that it could come out into more rural parts of especially impoverished nations, and a safety aspect that right now medical doctors are hesitant of giving the existing treatment because of the fear of adverse reactions.
There are other limitations. Current antivenoms are region and snake specific.
Current antivenoms are really geographically restricted to certain areas. So an antivenom that's made for Indian snakes, for example, won't work in North America for treating a rattlesnake bite. And that's because the venoms are very different between the snakes that are found in those regions. So what we're trying to do is really use scientific approaches to understand that diversity in venom toxins, identify which are the really key and important ones to neutralize, to knock out if someone's being bitten.
Snake venoms kill in different ways. Neurotoxins from cobras and mambas shut down the nerves that control breathing. Cytotoxins from puff adders destroy skin and muscle, leading to amputation. Hemotoxins from vipers stop blood from clotting, causing internal bleeding. And many snakes combine more than one method.
So there's no doubt that when someone is bitten by a venomous snake, you want to get them treatment in as soon as possible. And so access to that care, from the point where you're bitten to a health facility where you can get treatment is a really critical element. There are two bits to that. You can actually improve the transport of a sick patient to a big hospital, but you can also start to think about treatments that can be delivered at a local level.
That elusive prize is now within sight. Two teams, one from Britain and the other in Denmark, believe together they can deliver the medicine for one of the world's deadliest diseases. The team from Liverpool believe they are close to developing a pill that can be taken minutes after a bite, before the patient even reaches a hospital. It's made from existing drugs, originally developed for other diseases and now repurposed for snakebite. It works by stopping the venom from causing tissue damage and internal bleeding. It's already proven safe, so it can be given outside a hospital at the point of a bite, and it's cheap, easy to store, easy to take.
So these are synthetic chemicals, essentially, just like paracetamol that you might take for your headache. So this is a traditional, what we'd call drug. And so for snake venom in the past, we haven't used this type of molecule. What we're trying to do with research nowadays, whether it be with monoclonal antibodies or nanobodies that are being produced, or small molecule drugs, these can be produced synthetically. So we can make them in the lab, we can make them very consistent, and we can make that desired product we want much more inexpensively than we can with antivenom.
Some 600 miles away in Denmark, the ambition is the same, but the process and the result is very different. Here, the antivenom is grown in a laboratory. This works by neutralizing the venoms traditional antivenom can't. Scientists inject venom into llamas and alpacas, which produce small antibodies called nanobodies. Scientists then identify the best nanobodies and work out the DNA code needed to make it. By inserting that DNA code into specially grown cells, they can produce unlimited amounts of identical antibodies. This is then given as an intravenous injection at hospital, and it's effective against 17 of the deadliest snakes in Africa.
We designed the mixture and then of course tested it to start with in the lab, different ways of simulating the venom's effects and seeing can we neutralize that effect either on cells. Once we saw that it worked in the lab, we took it into so-called preclinical testing where we tested in mice to see can we save the life of mice that have been challenged with venom, and then after a time delay administered antivenom, or our, you could say, prototype antivenom. And what we saw was that our mixture of antibodies worked better than the existing antivenom on the market. It was more effective and it had broader coverage when it came to snake species.
But scaling up this revolutionary lab-produced antivenom is the next challenge. Here at this facility in Copenhagen, they're confident that it can be done. They're successfully producing it in much smaller amounts.
These cells are the cells that are producing the antibodies that are being used as antivenoms. They have been transfected, as we call it. The DNA, the gene for the antibodies, have been put inside each of these Chinese hamster ovary cells. Then we grow these cells to get enough of those. They divide about every 20 hours. Then you grow more and more, and then you grow, in this case, in 2 liters. You grow cells enough that you can produce enough of the antivenom antibodies that can be used for injecting a mouse or something to test the product.
This model bioreactor stores 2 litres. The ones used for manufacturing antivenom would need to be 10,000 times larger. Is it working? Are you producing antivenom?
Yes, we are producing antivenom. It's something we know can be achieved.
Snakebite remains a neglected tropical disease that kills and maims hundreds of thousands every year, and its treatment has not changed in over 100 years. But finally, there is hope.
I believe if you could make antivenoms safer and cheaper and at least equally effective, ideally more effective, yes, I do believe over the years we could save hundreds of thousands of lives.